Today we begin with chapter 6 in our lecture notes about semi-algebraic geometry. So that's the geometry of semi-algebraic sets and semi-algebraic functions. So actually the section we will treat today is 6.1 about semi-algebraic sets and functions. That means semi-algebraic functions, which we will introduce. So of course we did already a little bit of semi-algebraic geometry, namely that was in chapter 1.8, I think, so very early in this course. So for example here we had some result if R is a real closed field when pre-images of semi-algebraic subsets of R to Vm and the polynomial maps from R to Vn to R to Vm are again semi-algebraic in R to Vn. That was quite trivial, by the way. So semi-algebraic subset of R to Vm, of course, was a Boolean combination of sets defined by polynomial equations and inequalities in M variables. Okay, so but we had also already non-trivial result, namely that, for example, images of semi-algebraic subsets of R to Vn under polynomial maps are again semi-algebraic. And that was highly non-trivial. That was actually based on the real quantifier elimination. So the aim of this chapter is to do a little more semi-algebraic geometry. Just a little more, because you could do much more, but this is not the focus of this course. So we will do just a little bit, just the most basic things. So we will do this in the following settings. So we have a real closed field R, and also we look not just at semi-algebraic sets, but actually more generally at K semi-algebraic sets, where so you can specify that the sets should be Boolean combinations of polynomial equations and inequalities, where the polynomials actually have coefficients from K. That is often useful also, right? So and when I have this notation curly Sn, that should now denote for each non-negative integer n the Boolean algebra of all K semi-algebraic subsets of R to Vn. Well, that was previously, that was usually denoted as SNR, because Sn was previously standing for Boolean algebra of all semi-algebraic classes, right? More precisely, it was all K less than or equal semi-algebraic classes, where K less than or equal is an ordered field and fixed ordered field. Now for this K less than or equal, we could now take K together with the order that is induced from R, and so we could take for curly R, if you go back to these chapters 1.8, 1.9, we had this curly R, this set of real closed fields, or you might think of it as a class of all real closed extension fields of K less than or equal. But you could also take a more, you don't have to take all real closed extension fields. So you just as well, you could just take one real closed extension field, right? And that's in some sense what we do here, right? Because here in this section we are actually really working with semi-algebraic sets and no longer with semi-algebraic classes. And in this way, Vsn, if we take here just this one real closed field in there, then Sn is now actually what was formerly the SNR, and hence in some sense this notation is consistent. But you might just as well, you could just think that it's a change of notation if you want, which is convenient because then I don't have to write with R all the time, since I have fixed the R here for the whole chapter. Okay, so now let's go to the section that we will go through today. Semi-algebra section 6.1 about semi-algebraic sets and functions. So first a reminder, every K semi-algebraic subset of R to N is of this form. It's a finite union of sets of this form, where you have a set of all x in R to N that satisfy given a certain polynomial equation and finitely many strict inequalities. So these are and the polynomials, these equations and inequalities are over K. So the polynomials here are over K. That's why we call it a K semi-algebraic set. Yeah, that was, I mean, that was of course one of the first results which we had at that time for semi-algebraic classes, but in particular for semi-algebraic sets, for K semi-algebraic sets. Okay, and that was quite easy to prove, right? One of the tricks was that finitely many equations can be combined by forming a sum of squares of polynomials into one single equation and so on. So that was quite easy. And then reminder 6.1.2. So for all for all non-negative integers and for all semi-algebraic sets, subsets of R to the n plus 1, we have that this set, or a set of all x in R to the n, such that there exists a y in R, such that xy lies in S. Yeah, so that's an n tuple, and that's a number, and together that should denote the n plus 1 tuple, which arises from a concatenation. And here I have a set of all x in R to n, such that for all y in R, xy lies in S. That's both semi-algebraic again. And that was absolutely non-trivial. That required a real quantifier elimination. Okay, so well, the real quantifier elimination, we did it even for semi-algebraic classes, but if we do it for semi-algebraic sets, then that's what we need here. And you know about geometric intuition, because now we want to think more geometrically, is let's say we have here n equal 2, when we can when n plus 1 is free, and I can still draw three-dimensional. It's still not hard to draw three-dimensional pictures on a piece of paper or on a tablet. So so here I have maybe the x1 coordinate, the x1 axis, here the x2 axis. So here I have this x1, x2 plane. Yes, and then I have here the x3 axis, right? And the x1 and x3 axis lie on the plane of my piece of paper, respectively my tablet, whereas the x3 axis is orthogonal to it, right? But I draw it like this. Okay, and then I have some semi-algebraic set, right? So maybe for example I have a ball. Yeah, a union of a ball, maybe with a rotated cube. Right, so okay. And when I project it down on, so and then yes, this set here is of course a projection. So I project it down on the x1, x2 plane, right? So projection of this ball is a disk, and let me see the projection of this cube is more complicated. Maybe will be, don't know actually if it's possible, but let's say it could be a hexagon or something. Probably that's possible, right? A hexagon. Even with high probability, maybe it's a hexagon, I'm not sure. Right, so that's for projection, right? So that's for projection, and this, well, in this particular example here, if S is this orange set here, then this set would be empty, right? Because what is this set? Well, that's actually, you look at your object and you look which parallels of the x3 axis are entirely in your object, right? And then you draw all the intersections of these parallels to the x3 axis with the x1, x2 axis, right? So I think you know what I mean. So, okay, so, and that's by 1817 by the quantifier elimination. Now we define semi-algebraic functions or semi-algebraic maps, you could also say. So let m and n be non-negative integers, and let A be a subset of R to the m. Then a map F from A to R to the n is called K semi-algebraic if its graph is, which is a subset of R to the m plus n, is a K semi-algebraic set. And we say semi-algebraic. If we say just semi-algebraic, then exactly as we did for sets, we mean also for functions, we mean R semi-algebraic, when there is no restriction on where the coefficients of f could be in. And the domains of K semi-algebraic functions are K semi-algebraic. Well, that follows clearly by this quantifier elimination thing here, right? Because the domain of K semi-algebraic functions, so this would be the A here, is of course the projection of this graph onto the x coordinates, right? Onto the first m coordinates, and yeah. Here I said that I can project away one coordinate, but by iterating this I can project away finitely many, and so that follows from this quantifier elimination. Yes, and that's the explanation is here. Now, what we avoided so far is to equip a real closed field with a topology. So that's in fact one reason why we avoided is just because we were too lazy, but also this topology doesn't play the same important role as it does for real numbers, for example, right? But nevertheless, it does play a role, and therefore we equip now R with the order topology, which is generated by the intervals. That's just what it means that topology is generated. You remember that. That means it's topology generated by some subsets is the smallest topology, or you could say the coarsest topology containing the subsets, and that means actually that it consists of all unions, arbitrary unions of finite intersections of these generators. Okay, so now I look at the order topology generated by these kind of intervals, right? Where the endpoints A and B are arbitrary in R. So this consists of all x in R which are strictly between A and B. So actually A less than x and x less than B. So if A is greater than or equal B, then this is actually empty, but that's no problem. Okay, so and moreover, so yeah, and yeah, also if you can actually easily show that finite intersections of such intervals are again of that form, are again such an interval. And then, so that means actually a set is open in this order topology if and only if it's a union of such intervals, right? Moreover, we endow R2N with a corresponding product topology, right? Which is generated by these sets, right? Which are kind of distorted hypercubes or hypercuboids. Or since there is too much hyper, maybe people would just say it's cuboid. Okay, so for if R is the real numbers, the topology introduced on R to the n is obviously the usual Euclidean topology on R to the n. Well, the usual Euclidean topology, maybe you would introduce it using open balls instead of such open cuboids. Yeah, you easily show that amounts to the same thing, right? For example, because the maximum norm on R to the n is equivalent to the Euclidean norm, but in many other ways you can show it easily. Okay, so yeah, so now let such a semi-algebraic map be given, right? And when it is continuous, right? We have now here a topology on R to the n, right? A product topology of the order topology on R. And on A, of course, we have also topology, namely the one which is induced by the topology on R to the m. So it's the subspace topology, which makes A into a topological subspace of R to the m. And when F is continuous, that means pre-images of open sets are open. If and only if, and then now we come to a more traditional way of expressing continuity for all x in A and for all positive epsilon. I take them now from a real closed field, right? There exists a positive delta in this real closed field, such that for all y in A, if infinity norm of x minus y is, so that's the maximum's norm, right, is less than delta, then the infinity norm of f of x minus f of y is smaller than epsilon, where this is the infinity norm, right? So for k equals 0, if I'm looking at zero tuples, I have to be a bit careful that I don't write a maximum here because it wouldn't be defined. So that's why I make this case distinction. So that is an exercise, you really should do it. I mean, I did in the screencasts, I mean, not in the lecture notes, I guess, but in the screencasts, I did once a similar thing when we introduced the notion of continuity in for maps between topological spaces. I had here a similar reformulation of continuity in the case where the topology was induced by metric. And then I wrote here, if these were metric, I wrote here something like this. Instead, right? Now here, but you have to be careful, because at that time I had epsilon real and delta real. But that was just because a metric is real valued, right? If you could define a generalization of a metric, which is valued in an arbitrary real closed field. You could define that in the obvious way, and then if you do this, then you actually can probably more or less take the same proof. You have to be a bit careful in the details. So I don't do this now. You should do it as an exercise. So next proposition is that the following maps are Q semi-algebraic. Actually, that's the strongest form of semi-algebraicity. And but in particular, they are then semi-algebraic, right? And they are continuous. Okay, so where here I have a project topology. So here I have the order topology. Here I have a product topology of the order topology. Here I have induced topology from R, and here also, right? So these maps are Q semi-algebraic and continuous, namely the addition on R, multiplication on R, the inversion on R, absolute value on R, and square root on the non-negative elements of R. It is clear that these maps are Q semi-algebraic. For example, let's take the first map here, and why is this Q semi-algebraic? Well, the graph of it is the set of all A, B, C in R to the 3, such that A plus B equals C. That's just the solution set of a polynomial equation, and with coefficients in Q, right? So corresponding polynomial is P would be x plus y, or x1 plus x2 minus x3. So that's a polynomial over Q in 3 variables. And you could write this as P of A, B, C equals 0. Same thing for multiplication, and when here what's the graph here? So let's make this example here. Oh no, sorry, that one. So the graph here is the set of all AB in R2, such that A is not equal to 0 and A times B is 1. Again, this is a negation of a polynomial equation, and you combine it with and it's a Boolean operation with again with solution set of a polynomial equation. And yeah, I mean, the other things are also easy. I let you do this. So now, how do you show that they are continuous? So there are different ways of doing this. One way of doing it would be just to take to look at the usual proofs which you learn perhaps in your first year calculus course, and then you just try to do the same proofs over a real closed field. I mean, the proofs, with the proofs, I mean, of course, the proofs in the case where R is the field of real numbers. So for these, you have seen proofs in your calculus course, and then just try to do the same proofs. However, we are lazy, and we want to use the results which we know already for the real numbers, and to transfer it. And I apply essentially Tosca's principle. So by real quantifier elimination, the class of all the real closed fields for which the claim holds is semi-algebraic, right? because you know that something is that such a thing is, for example, this addition is continuous. Yeah, you can write it with these quantifiers here, right? And this maximum norm you can easily write also by a Boolean combination of polynomial inequalities and so on. So you can express everything in a semi-algebraic way, and when you look at a class of all real closed fields that satisfy this, right? Where you where we have for f here, for example, the addition in the first case here, and that's semi-algebraic by real quantifier elimination. It's a zero-ary semi-algebraic Q semi-algebraic class, right? It's a zero-ary. Let me write it down. A zero-ary Q semi-algebraic class, and we know that there are only two such classes, namely the class of all real closed fields or the empty class. Okay, and since it's non-empty because the real numbers are in this class, we know that all real closed fields are in this class. At this point, I would like to point out why I did not add here another true fact. Namely, another true fact is that the map from R to R, A maps to minus A, is also continuous. You might think I should have added this because here I have multiplication and multiplicative inverses. So I should have here addition and additive inverses. But I did not put this here for the following reason, because minus A is actually minus 1 times A. And in some sense, that this is continuous is therefore covered by the multiplication. You know, since multiplication here is continuous, and I can compose with a map from R to R2 that maps A to minus 1 comma A, right? And why is the map from R to R2 that maps A to minus 1 comma A continuous? Well, here I have a product topology, so that's the initial topology with respect to the two projections on the two components. Let me call it P1 and P2. And what I have to check is whether these composite maps here are continuous. But the first composite map here is just A goes to minus 1. It's a constant map, and which is trivially continuous. And the other one is A maps to A, which is the identity and is also continuous. Okay, good. So now corollary polynomial maps from an R to Vm into an R to Vn are continuous. So let's see. So here I did not give a proof, but let's do it as an exercise. So let me say I have such a polynomial map. What does it map? What does it mean that a map is polynomial? Well, that means that all components of it, that is, composite maps, if I compose it with projections on the ith component, that all these maps, that all these n composite maps here are polynomials, right? So that this is a polynomial map means that these composite maps are are represented by polynomials. Okay, and everything boils down to show that maps represented by polynomials are continuous. So polynomial maps from Rm to R, right? So I have immediately reduced to the case where n is 1. So, and I look at a polynomial map from R to Vm to R. Now, let's start maybe with a simple such polynomial maps, the ones which are given by x1, x2 up to xm, by these polynomials. Well, that's just the projections, right? So y is, for example, the ith projection pi, y is this continuous. Well, that's because that's by definition, because R2M is equipped with a topology that makes all these projections continuous, right? It's actually that's the initial topology with the projections, right? So it is the coarsest topology that makes this pi continuous. In particular, it is a topology that makes the pi continuous. So for these polynomials, for variables, it's clear. And when I need, for constant polynomials, it's also clear. And when I need just that if two maps from Rm to R are continuous, when their pointwise product and their pointwise sum is again continuous, right? And from this I get everything. So why is this? So let's do it with the product, for example, or with addition, for example. So let me say f and g are both continuous maps from Rm to R. Continuous. And y is f plus g continuous. Well, that's because the map from Rm to R2, that's the trick, right? X maps to f of x, g of x is continuous. And then I can compose with this map, with the addition map, right? And compositions of continuous maps are continuous. So I show that this is continuous, right? But this R2 here is equipped with a product topology again. So in order to check continuity, I look at the composite maps. I put here the projections. Yeah, and they are continuous because these composite maps here, the two composite maps are x goes to f of x, so that's f, and x goes to g of x, that's g, right? And they were continuous. And the same thing for the multiplication. Okay. So another corollary is that I could take, the polynomial map x maps to the sum of the xi squared. That's a polynomial map, so it's continuous. And I can compose it with the square root map. And then, because I'm in a real closed field, sum of the xi squared will be non-negative there. And I can take the square root of it, and so I can define the norm of x, or sometimes I write two norm of x in order to distinguish it from other norms. And note that this is not a norm in the classical sense. Classically, a norm is real number valued, and this is valued in this real closed field. So, but let me call it a norm, right? although it's not a classical one, when this is continuous, right? So, okay. So this norm is continuous. And because of this fact and 617, namely this reformulation of continuity in a quite classical way with infinity norm, there is, let's see what continuity of this means. There is to every epsilon a delta. So I use just continuity in here in 0. So I take x0, x equal to 0, right? And for y I take maybe let me rewrite it so that we don't get confused. So for x I take 0 here. Okay, so I have here 0, 0. And for y I write x, x. So when this becomes the infinity norm of x, and this becomes the infinity norm of f of x. Since now if I take a map into R1, then this becomes just the absolute value of f of x. And so I see that if you compare this, if you compare this now, okay, to every epsilon there is some delta, to every epsilon there is some delta, such that for all x in R to the n, right, if infinity norm of x is smaller than delta, when the absolute value of the norm of x is smaller than epsilon, but I don't need the absolute value here, of course, because the square root is already defined to be non-negative in the real closed field R. Okay, so now on the other hand, so I get this. On the other hand, I know that the infinity norm of x is less than or equal to the norm of x for all x in Rn. That's easy to show, right? So, I mean, for example, if x1 is the biggest component of x in absolute value, when the infinity norm of x is the absolute value of x1 and the absolute value of x1 is equal to the square root of x1 squared, and this is less than or equal to the square root of x1 squared, etc., plus xn squared. And you know, because in 147 we saw that the square root function is monotonous, is monotonously increasing. Okay, so you know that was here. Yeah, it's maybe going back to the very beginning of our course. We called this actually, there are so many names for it. What did we call it? We called it, it's actually here already on the first page. So we called it a homomorphism of ordered sets. Instead of what I just called monotonously increasing, I could say it was a homomorphism of ordered sets. Actually, I called it monotonic. Okay, good. And yes, so it follows that the topology on R to the n is also generated by the open balls you know, with some positive epsilon, where epsilon is now in this real closed field, not necessarily a real number, of course. And so ball with radius epsilon around the center y, right? So and that 617 holds also with a norm instead of infinity norm. So I could characterize continuity also here with a norm instead of the infinity norm, right? So that you know, that follows now easily from these things you play around with. So you use what I color here in yellow, namely this and this, right? And if you use these two, then you can easily see that this whole line here is equivalent to the same thing where I take here a 2 norm instead of the infinity norm, right? So you can also take a 2 norm here instead of the infinity norm. Easy to show, and also the topology on R2n is generated by these open balls. That I leave you also as an exercise. So now I claim that R2n is endowed with the initial topology with respect to all maps of this form. So these are just maps represented by polynomials. So that means polynomial maps into R. So it's endowed with the initial topology with respect to all maps into R. Okay, so well, it's endowed with what we know from by the definition. It was endowed with a product topology, so it was endowed with the initial topology with respect to a maps of this form, right? Or I could write it in this way, where P is one of the variables. Because these are exactly the projections, right? So product topology is here the one which is, it's the initial topology with respect to a projection. So I could write these projections in this complicated way by taking a polynomial which is actually a variable and saying its x is mapped to P of x. Good, it's the initial topology with respect to these maps. And so that means it's generated by the pre-images of open sets under these maps. And now if I take instead of this all polynomials, it does not change anything, right? Because I had seen that the pre-images of open sets under such a polynomial map is anyway open already in the product topology. So yeah, so I could say it's the initial topology with respect to this bigger class of maps here. Okay, and I don't think I don't know what I had in mind when I wrote that I use 6.1.11. I don't think it's useful, but maybe I was doing a different argument and I cannot remember it. Maybe you can make sense of it, I can't. So I will in the lecture notes, unless you protest, I will remove this in the lecture notes. Okay, because of Weber topology on R2n is obviously generated by these sets. Yes, okay. Viewing R2n in virtue of the injective map into a real spectrum of X, where X is mapped to this prime cone consisting of all f in Rx such that f of x is non-negative. We can view it as a subset of a real spectrum. The topology on R2n is due to be induced by the spectral topology. Maybe it's time for a reminder on the spectral topology, which is the usual topology on the real spectrum of a commutative ring A. So let A be a commutative ring, and we look at the real spectrum of A. And then the usual, that means the spectral topology in it is defined by, is generated, by all sets of this form, where the condition is that A hat of P is bigger than 0, and A ranges over all elements of A. Now here I have this more special case that I have here a polynomial ring, right? So I have here a polynomial ring, and I look at the real spectrum of a polynomial ring. Well, and then I can here write, it's perhaps, since polynomials are often abbreviated by f, it's perhaps more appropriate to write here f of p, and here I write that f ranges over polynomials. Okay, nothing happened so far. And yes, so what does that induce on the image of on the image? So what's the induced topology on the image of this map? Well, this is of course generated by the px, where x is in R2n, such that f hat, sorry, I forgot we had, f hat of px is bigger than 0. And f ranges over all polynomials. Oh, sorry, I wrote here the real numbers. That was, of course, not okay. I meant, of course, real closed field R. And then by virtue of this injective map, if I identify R2n with that, okay, so first maybe I rewrite this here. What does that mean? That means actually that f lies in px, but not in minus px. And f lies in px means that f of x is greater than or equal 0, but it is not less than or equal 0. So I can replace this by f of x bigger than 0, right? And now by virtue of injective map, I could say this induces the topology which is generated by these sets, right? And that's, of course, the initial topology with respect to all these polynomial maps here, polynomial functions here. Which is in fact the topology on R2n. So that's nice. So in this way, R2n is up to this identification, up to this injective map, is actually a subspace now. Before I could think of it as a subset. Actually, if you go back to 363, you see that we did this already. But now it's a topological subspace, right? So in 363, we had no topology, neither on R2n, neither on the real spectrum of a commutative ring. But now we have topologies on both of them. So we first introduced the real spectrum on a commutative ring. And in this section, we first introduced the topology on the real spectrum of a commutative ring. And in this section, we introduced also topology on R2n. And actually, it turns out that this is a subspace. And that's nice, okay? Now we want to speak about some basic operations that preserve semi-algebraicity, actually K-semi-algebraicity, and that's the next theorem. And so if first part is if F is a K-semi-algebraic map, right? Defined on some subset A of R2M and going into R2n, then images of K semi-algebraic sets are K semi-algebraic under this map, and pre-images as well. So images and pre-images under K semi-algebraic maps of K semi-algebraic sets are K semi-algebraic. Okay. Compositions of K semi-algebraic maps are K semi-algebraic. So if you have a function, so if A n is a subset of R2L, B of subset of R2M, and F from A to B and G from B to R2n are K semi-algebraic, when the composition G after F from A to R2n is again K semi-algebraic. If A is a K semi-algebraic set, then the K semi-algebraic functions from A to R form a subring of a ring R2A of all functions from A to VR. Okay. Of course, this ring here is equipped with a pointwise operation, so pointwise addition and pointwise multiplication. So that's a commutative ring, actually. And this is a subring. Okay, let's prove these things. So first, let A be a subset of R2M and F from A to R2n be K semi-algebraic. And now if I take a K semi-algebraic subset of A, if you want, then its image can be written as the set of all y in R2n, such that there exists an x in R2m such that x lies in B and x lies in the graph of F, right? It means just that f of x is y. That's clear. And but why did I write it in this strange way? Because in this way I have that F is semi-algebraic, means its graph is semi-algebraic. B was supposed to be K semi-algebraic, that was K semi-algebraic. So this is a projection of a K semi-algebraic set. And so I wrote this image as a projection of a K semi-algebraic set, and therefore it's K semi-algebraic. And that was not trivial. If you think about it, quantifier elimination is again behind this. And the other thing is similar. So the pre-image of C, you can write it as a set of all x to the R2m such that there exists a y in R2n such that y lies in C and xy is in the graph. So xy is is in the graph of F, which is a K semi-algebraic set. And yes, and this is for all C in Sn, also K semi-algebraic again. Now we prove B with the statement about the compositions. Okay, so yeah, I need again the same situation here. And then, you know, by hypothesis, the graph of F is K semi-algebraic subset of R to the L plus M, and the one of G is a K semi-algebraic subset of R to the M plus N. And actually the graph of composition can be written as the set of all xz in A cross R to the N, such that there exists a y in R to the M, such that xy lies in the graph of F and yz lies in the graph of G. And yeah, so it's again with quantifier elimination, respectively, with the fact that projections of such a K semi-algebraic set is again K semi-algebraic. I see again that this composition is K semi-algebraic, and K semi-algebraic functions from a subring here. So if A is a semi-algebraic set and K semi-algebraic set, and F1, F2 are two K semi-algebraic functions defined on this set A, then this function into R to the 2 is K semi-algebraic, and yeah, that's again easy to see because what's its graph? What's the graph of this function? So graph is a set of all x, y, z, such that xy lies in the graph of F1 and xz lies in the graph of F2. And so that's just a Boolean combination of two semi-algebraic things, as you see easily. K semi-algebraic things. Okay, so that's K semi-algebraic, and now I can compose this map with addition and multiplication, which are also K semi-algebraic by 6, 1, 8. So namely because compositions of K semi-algebraic functions are K semi-algebraic 6, 1, 8. Yes, so I use the first two statements here. Okay. Good. So now, so this is very natural, and so now let's turn to something a bit more complicated. So for subset of real numbers, you know, we have this notion of compactness. Maybe in your first calculus course, in your first analysis course, you defined, there are different definitions, but one of them you certainly know, or you certainly know it's equivalent to your definition, is that the subset of real numbers is compact if and only if it is closed and bounded, right? If and only if it's closed and bounded. Now we had defined compactness now in a more topological way. We would now say that the subset of real numbers is compact. Well, the real numbers are a Hausdorff space, so the question is just if it's quasi-compact. So a subset of real numbers is quasi-compact if and only if whenever I cover it with open sets, there is a finite subcover, right? So yeah, that's our topological definition, which we had here in 5121, right? So for subsets of topological spaces, we said when they are quasi-compact and when they are compact. And I think you should know that these two definitions, the first one was closed and bounded, and the other one was satisfying this property, that they are equivalent in the case of subsets of real numbers, and also probably you know it also for subsets of R to n. So our topological definition of compactness is just as good as the freshman's definition, let's say, of compactness in this special case. But now if we go instead of real numbers, we look at an arbitrary real closed field, since we have now defined a topology on this real closed field, right? The order topology. We have now a topological definition of compactness of subsets of R. And what we want to show is here that this topological definition is perhaps not so useful, right? So, namely, it has some unusual behavior. Namely, for example, the interval from 0 to 1 with endpoints included in R. So if R is the real numbers, then that's clearly compact. But it's not compact in this topological sense with respect to the order topology. If R is a non-Archimedean real closed, I mean R was anyway real closed always now, extension of of a field of real numbers when this interval is not compact. Indeed, we can cover it we can cover it by by some generators of our order topology. So take an positive infinitesimal epsilon. Such a thing exists, right? Because not every number, not every element of this non-Archimedean real closed field R is finite. So we take an infinite one, and then if we take its inverse, and maybe we flip its sign so that it becomes positive, when we get something in this maximal ideal, and of this subring of finite elements. And so these are the infinitesimal elements, right? These were the infinitesimal elements. So we take such an infinitesimal element, we fix one, we need just one. And then when we cover this interval by these intervals here, right? So you can think of it like you have here R, you have here 0, and you have here 1. When you take something really, really small, infinitesimally small positive, this is this epsilon. And when you, around each point of this unit interval, you put this infinitesimal interval here, right? And cannot even draw it. And they cover, of course, everything here. But, no finite, there is no finite subcover. Intuitively, that should be true. So there is no n in n and a1 up to nn with the same interval contained in this finite union. Maybe if you want an exact argument for this, we could work with a standard part, because, the interval from 0 to 1 in the real numbers consists of course exactly consists of the standard parts of this interval in the real closed field. Easy to show, right? And if you take this inclusion here and you take its image under the standard part, which clearly makes sense, when you get here the real interval from 0 to 1 in the real numbers, and easy to show, right? And here you get actually, because what's the standard part of this? Easy to show. The standard part of an element in this interval is the same as the standard part of AK. So I get that this would actually be contained in a finite set. So a whole interval from 0 to 1 in real numbers would be contained in a finite set of real numbers. That's of course absurd. So using the standard part, if you go back to the definition of standard part, that should be an easy exercise, and then you see it helps here to prove this formally. Okay, so this interval is not compact in this with respect to this topology we had introduced, the order topology on R. So that means perhaps that the topological notion of compactness is of limited use, probably very limited use. Good, so maybe we should therefore conceive another notion of compactness, some kind of compactness, and that's the idea, is just to mimic the definition which you have learned probably as a freshman, so at the university. So we do it just like you can do it in real numbers, although it's not the same as the topological compactness. So let A be a subset of R to the n, where R is this real closed field. We call A bounded if there is some B in R such that the norm of X, that's the 2 norm, right, is, and doesn't matter, you could also take the infinity norm as we saw. So if there is a B in R with norm of X is less than or equal B for all X in R, for all X in A. Good, so in 6.1.10 we had introduced this norm, that's the 2 norm here. And moreover, so it's important here that, so I don't take here positive integer, that would be even more restrictive. But, there can be infinite elements in this real closed field, bigger than any integer. So let's really take a B in R. It could be infinite, right? Moreover, A is called K semi-algebraically compact if A is bounded and closed. So closedness is really in the usual sense with respect to this product topology of the order topology. So here we take really the topological closeness, notion of closeness. Yeah, and the K here really plays, the only role it plays is just that that's to say that A is a K semi-algebraic set, right? So but the only role the K plays is the restriction that if I say K semi-algebraically compact, I mean it's a K semi-algebraic set which is bounded and closed. But for boundedness and the closedness, it doesn't matter what is K here. Yes, we simply say semi-algebraically compact instead of R semi-algebraically compact. Good. From analysis, one knows for real numbers, a K semi-algebraic set, subset of R to the n, is compact if and only if it is K semi-algebraically compact. That's what I said. You probably learned, hopefully, that compactness in our topological sense we have learned is in this case equivalent to bounded and closed. if you really did not learn this, then please look it up in some analysis textbook. So next proposition, we want to play around a little bit with this notion of boundedness, which we have just introduced. For so remember that we said that subset of R to n is called bounded if if a norm of elements is bounded, upper bounded by some element of real closed field. And now in the case of a K semi-algebraic set, I can actually also assume this bound to be from K. That's interesting, right? So all the other things are, I think, quite easy, but the main point is here that I can also write B in K here. Okay, so I guess that's not completely trivial, right? Because if you think about it, you could take real numbers, for example. So K could be real numbers, and R could be non-Archimedean real closed field. When the situation is as follows. So here we have R and the real numbers. Let me draw them maybe in orange here. Well, they don't somehow, it's not easy to draw, but they somehow don't go to the end, right? Because there are, of course, elements in R which are bigger than any positive integer. Let me draw here the integers, 1, 2, 3, and I have to, draw it in some strange scale, so otherwise it would never fit. Yeah. Okay, so and what I'm saying here is that there must be a bound even from K, right? So let's just take a subset of R. It can be bounded, right? Could look like, let me draw it in blue. Could look like, like this set. Could be an interval here, right? Like this, could contain real numbers. Okay, by the way, here are also lots of elements which are not real numbers, of course. Don't be irritated. This would, for this condition would clearly not be satisfied, right? But this condition would be satisfied, right? Because I can find such a bound B here, right? For example, here. But I can't find one within the real numbers. Can't find such a B within the real numbers. Okay, so, but this is because this is a K semi-algebraic set. Then this is actually equivalent. And now let us prove this. So, well, if A is the empty set, then all these conditions are trivially satisfied. So let me assume that A is not empty without loss of generality, then A implies B is directly by the definition. And B, if and only if C is directly by 6, 1, 11. Very easy to show, right? and E implies, of course, so D implies, of course, E, because the infinity norm is less than or equal the norm, the 2 norm, right? That was actually also mentioned in 6.1.11, right? And D implies E, and E implies C. That's trivial again, because K is a subset of R. Okay, so here we have this, and it remains to show that, for example, B implies D. So suppose therefore that B holds. So let's suppose that B holds. And we have to show D. Okay, the set. The set of all norms of elements X in A is certainly K semi-algebraic, right? So you could write it as, but that's non-trivial. Maybe it's K semi-algebraic by real quantifier elimination. Or I could say by the fact that projections of K semi-algebraic subsets of are K semi-algebraic, namely because yes, so maybe that would perhaps in fact be more appropriate to cite 6.1.2 in fact, right? So maybe I should here 6.1.2. Maybe I will change this in the. Both is okay, but I mean, it's actually not a full force of real quantifier elimination. It's just a reminder 6.1.2. Okay, so why? Because you could say this, you take the set of all, so this is the set of all y in R such that there exists an X in R to the n, such that X lies in A, and y is non-negative, and y squared is the sum of the xi squared. You know, that's a semi-algebraic condition, that's a semi-algebraic condition, that's a semi-algebraic condition even given by a polynomial equation, and that's finitely many existential quantifiers. Hence S can be defined by finitely many polynomials. So 186, because you know it's a subset. Okay, 186, so you know, yes, can be defined in such a way where only finitely many polynomials are involved, and whether a point lies in or not depends just on the signs of these polynomials, right, at this point. And important that these polynomials have coefficients in K. And by lemma 153a, so we see that the sign of such a polynomial, if you are, you know, so the coefficients of a polynomial are now in K, and so this bound here is in K still, right? Is in K, and yes, and so you know that you know you know that the sign outside when the absolute value exceeds, for example, some element from K, when the sign of these polynomials does not change anymore, right? Yes, or depends just on the sign of a point where you evaluate. Okay, so so we find some B such that each of these polynomials, let's say from K bigger than 1, such that each of these polynomials has constant sign on the interval B infinity, from B to infinity. So that means either the whole interval lies in S, or nothing of this interval lies in S. No point of this interval lies in S. But the latter is impossible, since otherwise it would not be bounded. I have now assumed that I have that B holds, right? Okay, so yeah, hence nothing in this interval lies in S, and when I'm done. So that means the norm of X is less than or equal B for all X in I. Okay, so now comes the main theorem. Let A be a subset of R to the M, and suppose F from A to R to the N is a semi-algebraic map and continuous. When for every semi-algebraically compact set B, the set F of B is also semi-algebraically compact. So this will actually be a very useful theorem, and before we prove it, maybe I tell you a theorem which we did not speak about, but which you might know about. Okay, so if M and N are topological spaces, and if I have and if M is let's say quasi-compact, and if F from M to N is continuous, when the claim is that F of M, the image of F, is also quasi-compact. In some context, you have probably seen something like this. Don't know if you have seen it for topological spaces. And the proof is in fact easy. So let be a cover given. So so I write it shortly. So let Fm be covered by a family of open sets. Maybe let me call it Bi open in N, right? And I have to show that there is a finite subcover. And so I take, well, I actually see that M is the union over the pre-images of a Bi, right? Because if I have a point in M, when its image is in one of the Bi's, that means this point is in one of these pre-images. Now, but since these Bi were open and F was continuous, all these are open subsets in M, and therefore there is a finite subcover, right? So there is a finite subcover, and then from this you get the corresponding finite subcover here. And okay, and when you are done. And this is an analog to this classical topological theorem. It's an analog, but since our definition of K semi-algebraically compact was totally different, and in a general case not equivalent to a topological definition, we need a totally different proof. And so we will actually reduce everything by Tarski's principle to a case where real closed field is a field of real numbers, and for real numbers we know the theorem already, right? Because for real numbers we know that the subset of real numbers is compact if and only if it is K semi-algebraically compact from 616. So we will have to encode everything in a way so that we can reduce it to a case so 6116 I wanted to say, right? So because of this we know it already for real numbers. Okay, so because of this and what I've just shown, or due to your analysis course, right? You have certainly seen that compact subsets of R to Vn, where R is real numbers under continuous maps into some R to Vm, or so images of compact sets in this setting are compact. You have certainly seen this in your analysis course. So we will reduce it to what you know from analysis. And so we have to think about how to formulate this somehow semi-algebraically so that we can apply Tarski's principle. Okay, so let's now go into a proof. So if B is a K semi-algebraic subset of R to Vm that is contained in A, then its image under F is a K semi-algebraic, just because in general images of K semi-algebraic sets under K semi-algebraic maps are K semi-algebraic. That was 6113A. That was part of 6113A. The same is true for pre-images. So since F is K semi-algebraic, so okay, so now we have to show that it's K semi-algebraically compact. The only thing that remains to show, since we know already that the image is K semi-algebraic, is that it is bounded and that it is closed, right? And that has nothing to do with K anymore, right? So so we could actually assume now that K equals R, because if F is K semi-algebraic, then it's also semi-algebraic, right? When it's also R semi-algebraic, and if B is K semi-algebraic, then it's also R semi-algebraic, and so we can assume K equals R. So forget about K now. And now we fix, so now how can we, so now our strategy is to encode the validity of this theorem over R. So what remains to show is that the image is closed and bounded, right? So we can now concentrate on that. So maybe we write here now closed and bounded, closed and bounded in R to Vn, right? And we try to encode this in a semi-algebraic way, so that we can then speak about all the real closed fields where this is true somehow. But this wouldn't make too much sense if A is a fixed subset of R to Vm, right? When I cannot vary the the real closed fields where it is true. That doesn't make too much sense, but that's the strategy, right? Because we want to say, oh, with this theorem, I mean the remaining part that is to show, this orange part, this is true for all real closed fields. And yeah, so by the way, I can now just say semi-algebraically compact, which means are semi-algebraically compact, right? And in order to speak about all real closed fields, I should no longer fix the real closed field, and I should therefore no longer fix VA and no longer fix VF, right? So I'm rather now looking at something like for all, actually, maybe we should write this even here. So for all real closed fields, let me just write curly R, and for all A is, and for all M non-negative integers M, and for all A subsets of Rm, and for all maps, semi-algebraic maps from A to Rn, which are continuous, and for all and for all semi-algebraically compact sets B, the set f of B is closed and bounded in R to Vn, right? So so now how can I speak? So sometimes we had already statements where I somehow managed to speak about polynomials, right, of some bounded degree. Here I want even to speak about semi-algebraic functions now and semi-algebraic sets, right, for f and B. Yeah, and how can I speak about them in my language? You know, the language that allows quantifier elimination later. Well, the trick is just to speak about polynomials that define this set, right? And but I don't know their degree. I don't know how many they are, and so on. So I fix kind of a complexity bound, right? And so actually, I will introduce here another thing, and a kind of complexity bound. So I have now something. I have now several sorts of quantifiers. So I have the quantifier for all real closed fields, right? So that plays a very special role, because that will I will actually look when at the set of all real closed fields, or the class, if you want, that satisfy what I want, right? So that quantifier will play a very special role. That will not be a problem. When I have a quantifier over non-negative integers, right? So for all m in n0. So you know, this is not the kind of quantifiers I can eliminate. I can only eliminate quantifiers that range over the real closed field. So that plays a special role, but that was not a problem, because I will just, you know, split up the theorem for each fixed m. I will look at the theorem. So with red quantifiers, they will just be handled by splitting up everything, right? We will see this. So they will not directly be implemented, but for each fixed m, I will formulate something, right? And then I have here. Now I need here here's a quantifier. Okay, so I introduce an artificial quantifier now, a new quantifier, namely kind of complexity bound n. Positive integer probably, right? So let's see. Yes, the positive integer. So that's new, and the aim of this is that I can now speak about. I can say I have a certain number of polynomials, maybe n, or actually it will be n squared or something like this. We will see in a minute. And all are of degree at most n, right? And the semi-algebraic function is given by, is somehow defined by these polynomials, and in some way, and so we will see this in a minute. And when I speak about the coefficients of these polynomials, so speaking about polynomials of restricted degree can be done by speaking about the coefficients. So this capital N will serve as a bound, more or less, for the number of polynomials, or the number of polynomials will depend in some way on it, and the number of polynomials that defines this f, for example, and also the b. Actually, the b also is defined by polynomials, and so it will be complexity bound for the degree of these polynomials, for the number of these polynomials, defining a f and b and so on. Right. So that's my trick, and then let's see. So these are the red quantifiers. They are not our real closed fields. And then there will come many quantifiers over the real closed field, right? Many. And not just universal quantifiers. A lot of other things will come. But in the end, everything will be good. Okay, so you don't have to understand all right now, but it's just to prepare you a little bit what more or less now comes. Okay, so now so that's why I say here we fix this complexity bound, and we fix m and n actually, that we can fix, right? N also, right? So maybe I should have written here first. Doesn't matter in which order, but maybe it's if I put here the m, then maybe I should put here also the n first. Doesn't really matter, and then comes the complexity bound, right? And and actually these quantifiers here, they are handled by fixing the things, right? I fix m, n, and n, right? So maybe it would actually be better to put the blue thing below here. So let me see. I can move this here. Move this here. And maybe move it back here. Okay. So this will be handled by fixing the things and doing the proof for each fixed m, n, and n. I mean the proof, I mean the reduction to the case of real numbers for each fixed m, n, and n. And then this will be handled by just looking at the class of all real closed fields that satisfy the thing. And these quantifiers, etc., all that comes here, I did not show you yet, that will be handled by real quantifier elimination. So this is also not a problem. Okay. So it suffices to show the following. And now maybe I uncover everything, right? Not everything, maybe. Okay. So for all polynomials f1 up to fn, g11, g12 up to g1n, etc., g21, g22, etc., up to gnn. So these are n squared g polynomials here. Okay, and these polynomials actually they are of restricted degree n. So that really I can handle them. So because I could, instead of speaking about the polynomials, I could speak about their finitely many coefficients, right? So for all these polynomials, and these are polynomials that should define this graph of f, right? So they are, so how many variables do I need? The graph of f is a subset of R to Vm cross R to Vn. So I need, let's say, mx variables and yn variables. And then I need other polynomials for defining this set B, right? And I take just the same number of polynomials. I call them fi tilde and gij tilde, and of the same maximum degree, but this time only in the x variables, because that's a subset of A. So they should define a subset of A. So that means a subset of R to Vm in particular. So if we set gamma to be the semi-algebraic set defined in this way by these polynomials, right? And it's actually no big restriction to think about only this way, right? Because I know that each semi-algebraic set can be written in this way. So that is 611. Let's look at that again. So that was a reminder, 611. Yeah, that was this reminder here, right? So if we set this gamma to be this, and we set A to be the domain of this semi-algebraic map, right? And we set B to be the set defined by the tilde polynomials. Then one of the following things must happen. Namely, gamma is not the graph of a continuous function from A to R to Vn, right? So that you can, so maybe you do first as an exercise, you could say gamma is not the graph of a function from A to R to Vn. You know, that's actually easy to do. That's something like saying for each x, y, and so maybe it's a bit easier. I say that it is the graph of a function, and then you could negate this, right? That it is the graph of a function from A to R to Vn. Well, A was already defined as this, so I don't need to write that it's defined on the whole of A, and I don't need to write that it is not defined on a bigger set, right? So that's automatic. So I just need to write that that for all x, y, and that for all x in R to Vm, and for all y prime, both in R to Vn, if xy is in gamma and xy prime is in gamma, when y equals y prime, component-wise, of course, right? Equality of tuples is, of course, component-wise equality, but yeah, but you can write this down, you know, really component by component as a finite conjunction. And yes, and also that for all x in R to Vm, there exists a y in R to Vn, such that xy lies in gamma, right? So this and this, right? Yeah, so that means that it is a function from A to R to Vn, and then that it defines a function from A to R to Vn, and then, you know, this that it is continuous, you can also express, right? That's an exercise you could, by this kind of thing here, right? And then negation, by negation I can express that gamma is not a graph of a continuous function from A to R to Vn, or B is not a subset of A, right? So that of course you can also express with quantifiers, right? You could say not for all x in B, right? And actually being in B, right, you can express with these with this expression here, right? So yeah, I mean that's semi-algebraic. Okay, so for all x in B, x in A, right? And so on, then you can, or B is not closed in R to Vm. Okay, maybe that's a little bit, there are several ways of doing this, but one way would be to say that there is something in a closure that is not in B. Being not in B is easy to write, being in the closure would mean that whenever you take a little cube or a little open ball around the point, then there is a point of B inside, right? Easy to write down, right? You write for all epsilon bigger than 0, etc., 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 etc. B is not bounded in R to Vm, also easy to write down, or B is not bounded in R to Vm. Or finally, now I have just to express that f of B is closed and bounded, right? And f of B, of course, you can write in this way with these finitely many, these are m existential quantifiers here and so on. Right, and so that expresses exactly what we want, and of course for fixed mn and r, so and we now in addition no longer fix r, one can easily figure out why the class of all real closed fields R for which star holds. For which star holds is semi-algebraic, right? You have to formulate it, and you can eliminate the quantifiers, etc. For this aim, one applies many times the real quantifier elimination, for example, for introducing the finitely many coefficients. Yeah, about the polynomials, I speak, of course, by speaking about their coefficients, right? And by 185, star now holds either for all or for no real closed field R, right? That is this 185. It was a long time ago. It was this Tarski principle. The empty set and the whole of curly R are the only zero airy KP semi-algebraic classes. Okay. Therefore, it is enough to show star for R equal real numbers, right? But we knew this from analysis. We know this from analysis, yeah? I have already told about that. In 6.1.16 we formulated already. 6.1.16, yes. Yeah, because K semi-algebraic compactness means compactness, and that images of compact sets under continuous maps from some R to Vm into some R to Vn, where R are now real numbers, that images of compact sets under continuous maps are compact in the setting where the map goes from R to Vm to R to Vn, and R are real numbers. That is known, right? And I actually proved this because I proved that topological compactness, the usual compactness is preserved. And since this is equivalent to a semi-algebraic compactness in the case where R are the real numbers, yes, we have it. Yeah, and this equivalence is 6.116. That was not proven, but that should have been proven in some analysis course, which you have already heard in the first years. Okay. Good. So that was main theorem. So images of Semi-Algebraically compact sets under continuous Semi-Algebraic maps are Semi-Algebraically compact. Okay, so and note that okay, so that's the nice theorem we have proven, right? And so now so now an exercise we open respective, just a exercise on the order topology on R. So we open and close semi-algebraic subsets of R are exactly the finite unions, well, in the case of the open semi-algebraic sets, finite unions of pairwise disjoint sets of this form with A, B in R. Yes, and we because they are yes, so that's an easy exercise, and yes, and we closed semi-algebraic subsets are exactly the finite unions of pairwise disjoint sets of a form of this form. That's an easy exercise. I let you do this. And the semi-algebraically compact subsets of R are exactly the finite unions of pairwise disjoint sets of this form. That's very easy to prove now, right? Because I know already how the closed ones look like, and when I need to just to assure that they are bounded. Okay, good. Thanks, and hopefully see you next time when we go to Bavoya-Savage inequality. Goodbye.